No, I'm not showing you the Game of Thrones. Okay, this is the observation. This is a simulation corresponding to this black hole. And of course, in a simulation, you have full resolution of everything. But the telescopes we have, they have a finite resolution. And if you smear the image, taking into account the finite resolution of the telescopes, this is what we expected to have. There is still the question of here, there seems to be a less intense region. We don't see that in the simulation, but I don't know, maybe it's the image. This is observation. This is simulation. So basically, if you are asking that, what's the difference, then probably the theory is correct. Now, any questions on these operator concepts?
Momentumun direkt yukarıda hissi bulduğumuz gibi bulamamızın sebebi momentumun bir uncertainty'si olması. Yani hisse bağlı fonksiyon olarak direkt yazamamış.
Well, if you are talking about position, you cannot talk about momentum. But of course, there's an alternative picture. You can also talk about momentum. I can talk about momentum. You see, here I'm talking about the probability of observing the particle at a given point, x. I should be able to also talk about the probability of observing the momentum of the particle to be p. Well, that is where the Fourier series comes into the game. You see, if you write psi of x and t as the integral, well, what Fourier theorem tells us is that, what Fourier series tells us is that if you have a periodic function, you can write it as a sum of sines and cosines. What Fourier theorem tells us is that if you have any function, you can write it as an integral of sines and cosines. Or instead of sines and cosines, we quite often use the exponentials. So it's dp e to power I p over h bar x phi of p. What Fourier theorem tells us is that this is always possible. But here, phi of p, t squared, is the probability density of momentum p. And now I can write the expectation of the momentum. This time it will be just dp phi conjugate as a function of p and t. Here I have just the p. I just insert the momentum. But then since I have the momentum, I cannot talk about the x. So how do I write the expectation value of x? dp phi star of p of t h bar over I derivative with respect to p of phi of p of t with an additional minus sign. You see, if you write your wave function in terms of momentum, the momentum is simple. But the position is not so simple. If you write your wave function as a function of position, then position is simple, but the momentum is not so simple. What do you remember from your linear algebra course? In terms of the eigenvalues, eigenvalue equations. You see, when we say h, let's say the momentum. Now, we already said that, looked at some examples. We had the momentum operator. If the function is such that this is satisfied, you see, just pay attention to hats. This is the operator. It has a hat. That will be the common, the general notation we will be using. This, there is no hat. This is just a number, like 5 kilogram meters per second. This is our eigenvalue. This wave function is the eigenfunction. And if there is a particle whose wave function is given by this one, and if we measure its wave function, its momentum, if we measure the momentum of a particle described by this wave function, what we will measure will be this one. So in that case, we will definitely measure its momentum to be p. Yes. Exactly. Schrödinger equation is linear. Meaning that if we have two solutions, then their sum, in fact, if you multiply them with anything that you like, is also a solution. Now let's look at the probabilities. What is the final probability? I had two wave functions. I just summed them up. And now I'm asking you the probabilities. Well, this is a squared psi1 squared plus b squared psi2 squared plus a star twice the real part a star b psi1 star psi2. If we just take the square. Now let's just look at the case a is equal to b is equal to 1. Again, just for simplicity. Now psi squared is psi1 squared plus psi2 squared plus twice the real part of psi1 star psi2. You see, this is the probability that only the first wave exists. This is the probability that only the second wave exists. So classically, we would add the probabilities. Probability of one case, probability of the second case. That is what we would expect classically. For example, in the case of the double slit experiment. We can say this, the wave function coming from this slit, we can call it psi1, and the wave function coming from the other slit will be psi2. So the total wave function here will be psi1 plus psi2. The total probability is not just the sum of the probabilities. There is also this term. In fact, this term is what causes the interference effect in the interference of the electrons, for example. So it's the linearity of the Schrödinger's equation which leads to the interference even for what we call particles, like the electron and the atom.
Bu operatörleri de matris olarak düşünebilir miyiz?
Yes.
Eğer string'le slit arasında mesela gaz olsaydı, o gaz atomlarını, gazın içindeki atomları da wave function'larını bu deneyimin içine katmamız gerekecek miydi?
Well, we will hopefully, towards the end of the semester, discuss what happens if we have more than one particle in our system. But let's just, for the time being, let's leave them to later on. But the short answer is yes. Quantum mechanics tells us that we have to sum the probability amplitudes, which are called the wave functions, not the probabilities. And summing probabilities, you see this term, the presence of this term is the difference between the two. we are not just summing the probabilities. There is this additional contribution. In fact, this is the reason why we observe interference in electrons also. We are not just summing the probabilities, we are summing the amplitudes and then calculating probabilities. Well, just take the square of A psi 1 plus B psi 2. It should be. It's the absolute value squared. That's the definition of the absolute square. No, A star B, what you will obtain is this one. This is the full expression we will obtain. This last two terms just give me twice the real part of each one. The imaginary parts, they just cancel. If I don't write the real part, I have to write both terms explicitly. You see, this term is not necessarily a real number. It's not a real number. This is not a real number. Their sum is always a real number. So if I just want to remove this term, then I have to make sure that I only take the real part. Other questions?
Sadece burada notasyonda neden birisinin şeyini aldık? Final conjugate'ini. Real part'ını yazarken conjugate almanın belli bir significance'ı var mı?
Because without the conjugate of parts of it, it won't be the same real part. You see, A star B plus AB star, this is twice the real part of A star B, which is not equal to twice the real part of AB. These two things are different. No. No. You have a sign difference. Do it explicitly. You see, okay, complex calculus is not the subject of this course. Let's leave the complex calculus aside. This is the result of that complex algebra. If you have any questions, make some explicit examples. And if you still have questions, ask them in auto class, but let's go back to physics. Let's leave aside the algebra. Now, let's kind of complete our recipe. Okay, here we have this correspondence. We have classical objects. In quantum physics, we have the corresponding operators. So we use the operators. What are the outcomes of our measurements? For example, the energy. Well, if we solve this eigenvalue equation, this is the eigenvalue. Well, we have actually, in fact, seen some cases where, at least one case where we solve this equation, is the eigenvalue and possible eigenvalues is equal to the possible outcomes. For example, in the case of the particle in a box, we had seen that this equation has a solution only if E is equal to h bar squared, or let me write it this way, 1 over 2m n over pi L h bar n over h bar squared pi n over L squared. Only for these values of E, this equation has a solution. So these are the eigenvalues, and hence if we have any particle in this box, if we measure the energy of this particle, the outcome will always be one of these eigenvalues. Well, if we measure the momentum, what if we measure the momentum? Well, let's see. Again, if we, as an example, if we go to the particle in a box, let's see. Okay, first, the possible outcomes will be the eigenvalues of the momentum operator. What are the eigenvalues of the momentum operator? Well, let's write the eigenvalue equation first. This is our eigenvalue equation. Well, our operator is h bar over I del over del x of psi is equal to p times psi. Or the derivative of my wave function should be equal to I times p over h bar times my wave function. So I should find a wave function whose derivative should be equal to my wave function itself with some coefficient. And the function that satisfies this is nothing but the exponential. These are the eigenvalues of these are the eigenfunctions of my momentum operator. Now let's look at the particle in a box. Well, the wave function we had found for the energy levels was this one, 2 over L sine n pi over Lx. This is the wave function. Well, this doesn't look like that one. So if I act with my momentum operator on this one, this is not some number multiplied by my wave function. So this is not satisfied. So we say that the particle described by this wave function has no definite momentum. It's not a momentum eigenstate. But what we can still do is, this is square root of 2 over L. Well, sine is e to power I n pi over Lx minus e to power I n pi over Lx over 2 I. What I write over here is nothing but sine n pi over Lx. So this is equal to square root of 2 over L e to power, or let me write the constants first, 1 over 2I e to power I n pi over Lx minus square root of 2 over L 1 over 2I e to power, now here there is a minus sign, minus I n pi over Lx. Yes. 2I. This difference just gives me 2I times the sign. Do the algebra on paper and you will see. So you see here we have a wave whose momentum over h bar is n pi over L. And here I have another wave whose momentum over h bar is minus n pi over L. So if I have a particle described by that wave function, and if I measure the momentum of this particle, not the energy, the momentum of this particle will be either this one or this one. I don't know which one. At every measurement, I will probably get a different outcome, but To determine the probabilities, what we do is we just compare the overall coefficients. They are equal. The probabilities will be proportional to these coefficients absolute squared. So with 50% probability, I will measure a momentum equal to h bar n pi over L, and 50% probability, I will measure a momentum equal to minus h bar n pi over L. Well, does that make sense? Well, if I know the energy of the particle, I know the magnitude of the momentum, classically. P is equal to square root of P squared is 2me, or P is equal to plus or minus 2me. So if I know the energy, you see this wave function is a state that has a definite energy. And the energy of that state was h bar squared over 2m multiplied by n pi over L squared. This is the energy. It has a definite energy, and that energy is that one. But that state doesn't have a definite momentum. There are two possible outcomes if I do the momentum measurement. One is this one, the other one is this one. And both of these measurements basically correspond to these two possible cases. If I know the energy, the particle might be moving towards the left or towards the right. There are two possibilities. And in this particular case, since these coefficients are equal, the probabilities of the momentum are also equal.
Is there any way that the two terms might be equal?
Might be unequal.
Might be equal. The ones that you said are not equal. If we were to reduce the...
You mean these ones?
The ones that are very high.
Even more. You mean here? You see, in this particular example, a state having a definite energy cannot have a definite momentum. If we look at, you see, you can look at this state singly. Let's say psi plus. This is just one part of the wave function I studied. Well, if I act on this with the momentum operator, I get n pi h bar over L times my wave function. That is why I say that this wave describes such a wave packet. But that doesn't satisfy But then it doesn't satisfy this equation, this one. So this wave function does not have a definite energy.
In that case, the original is equal. In this case, the original terms are equal.
What do you mean equal? Which terms?
Then if the energy is not definitive, then the momentum will be.
Well, not necessarily. Let me also write you a third wave function. So let me, if I act with the momentum operator, this will not be equal to some number times psi prime. Because the first term will get a factor n pi h bar over L. The second term will get a different factor, a different coefficient. So when I act on this wave function with the momentum operator, I don't get the same wave function. And similarly, h acting on psi prime will not be equal to some number multiplied by psi prime. Then you can ask the question, is it possible, you see, we have seen three cases. We can come up with wave functions that have a definite momentum. but then they will not have a definite energy. We can write down wave functions that have a definite energy, but then they will not have a definite momentum. And we can write down wave functions that have neither definite momentum nor definite energy. Is it possible to find a wave function that has a definite energy and definite momentum? There is no uncertainty relation between energy and momentum, not in a general one. For this particular problem, it's not possible. You see, for example, delta P and delta X, their product is always larger than or equal to h bar over 2. In this problem, I can come up with an uncertainty relation which will relate delta P and delta E. But for a different problem, that relation will be different. For some problems, delta P times delta E can be 0. But in this problem, it cannot be 0.
Will it be possible for us to find such a relation if the potential walls were not infinite?
No. Do you remember Taylor expansion? So let's see, psi of x plus delta is, this was psi of x plus derivative of psi at x multiplied by delta, etc. Well, let me write it in this form. Psi of x plus delta times the derivative with respect to x of psi of x plus the next term will be 1 over 2 factorial delta times the derivative with respect to x squared times psi of x, etc. Or let me write this symbolically. 1 over n factorial delta times the derivative with respect to x to the power n psi of x. This is the Taylor expansion. Let me just finish this and then you can ask. Let me write it slightly differently. 1 over n factorial h bar over I del over del x I delta over h bar to the n psi of x. Let me still continue a bit further. 1 over n factorial I delta over h bar. That is the momentum operator. But you see, this is nothing but the Taylor expansion of the exponential. Now, what was this? I mean, if you are not following, don't forget, don't worry. You will study these in 300 and 431. This is just because I didn't want to leave the question unanswered. You see, the momentum operator, what it does is it translates your wave function from the point x to the point x plus delta. Let's look at this problem. I have a potential at the point starting at x is equal, I have a well starting at x is equal to 0 to x is equal to L. If I translate my system, it will be a different system. Basically, that is the reason why in this system, I cannot have a definite energy state, which is also a definite momentum state. In fact, as long as I have a potential which changes as I translate it, then there will be an uncertainty relation between energy and momentum also, which will be non-zero. Okay, so there's a question over there. And I'm not going to follow up this line. If you have questions, we can discuss after the class. Not about this one. Okay. Definitive of what? Yes, that's definite. I mean, if I have a definite energy state, that will be the case. And that's not always the case. Well, let's look at a different problem. You see, the walls are not infinite this time. Let's see what will happen here. Well, of course, the potential, you can choose the zero of your potential wherever you like. You can, if you like, put the potential over here and put your V0 over there. And V0 goes to infinity, would be just our infinite potential well case. But let me put the 0 over there. It doesn't really make any difference, just a shift in the potential energy. So this is U is equal to 0. This is U is equal to, let me call it minus U0. You see, if you remember, let me write down the equation that we are trying to solve now. This is our new eigenvalue equation. And the possible eigenvalues will tell me what the energies of my particle will be, can be. Now let's first of all, divide this problem into 3 regions. Region 1, region 2, and region 3. Now if you remember, in our earlier case, walls with an infinite walls, we said that in region 1 and in region 3, the potential was infinite. And since the potential was infinite, this term was infinite in those regions. If I want to find a finite E, I should make sure that my wave function should be 0 outside my well. But now the potential is not infinite anywhere. So my wave function in region 1 and region 3 need not be 0. There is no such requirement. Well, classically speaking, classical physics tells us that if the energy of my particle, in this case, if the energy of my particle is negative, that is the total energy, kinetic plus the potential, then my particle should be in region 2. It cannot be in region 1 and it cannot be in region 3. Now, at least my equation tells me at this point, since the wave function is non-zero in region 1 and region 2, there is a finite probability of finding the particle in region 1 and region 3. Although its energy will not be positive in that. Its kinetic energy will not be positive. Now, we will see. So let's start the solution a bit and then ask your questions. Now let's say this is our x-axis. Let me call this as x is equal to 0. This point is x is equal to L. In region 1, let me start with region 1. Well, in region 1, my potential is 0. This is 0. So the equation will be simple. Minus h bar squared over 2m d squared phi of x by dx squared. This is equal to E of phi of x. Well, I should also treat the cases E larger than 0 and E smaller than 0 separately. Now I will, because if you remember before when we were looking at particle in a box case, the minimum of the potential was at 0. We said that the energy has to be 0. The energy cannot be negative. But in this case, there is no such reason. Even classically speaking, the total energy of the particle can be negative. So the particle will be inside my box. Or the total energy of the particle can be positive. It can be just going straight through. You see, the energy is the kinetic energy plus the potential energy. Now, the kinetic energy, at least in classical physics, let's say, has to be positive. But the potential energy can be both positive and negative. You see, here we just fixed the 0 of our potential such that this level has 0 potential. So in the box, the potential energy is minus U0. It's negative. So if the kinetic energy is less than U0, then the total energy of my particle is negative. There's no problem with that. Now I'm asking the question, okay, in classical physics at least it should be possible. The kinetic energy can be 0, a typical example. kinetic energy can be 0. The total energy will be just the potential energy. If my particle is somewhere over sitting at this point, the total energy will be minus U0. Now we asked a similar question in quantum physics. Is it possible? You see, one thing we had seen in a particle in a box was if you confine your particle, then it cannot have 0 kinetic energy. Because the uncertainty principle tells me that if I say that my particle is somewhere here, then the uncertainty principle says that it cannot have 0 momentum. If it cannot have 0 momentum, then it should have some finite kinetic energy. It cannot have 0 kinetic energy. Well, in this problem, if my particle is somewhere in the box, I'm confining it, so the kinetic energy cannot be 0, then there is a question, can the total energy be negative? If the kinetic energy is too big, then the potential total energy cannot be negative in quantum physics.
Bu discrete verileri taşımak,
Discrete? Well, I don't know if it is discrete or not yet.
assume ettiğimiz önceden n'le değişen, n integer.
No, that was the particle in a box. I don't know whether the energy is here will be discrete or not. Even that I don't know. I'm just guessing that in general, if your particle is, you know that your particle is in a finite region, either restricted by walls or by some potential energy, then the energy levels will turn out to be discrete. It's a general feature. So I know that the negative energies here will be discrete, if any. The positive energies will be continuous. It can have any positive energy.
Dalga fonksiyonunun doğası gereği eigenvalüler oscillate eden bir şey için discrete gelmek zorunda kalmıyor mu?
No.
Initial verileriniz böyle.
You see, my free particle, quite often we were discussing the free particle.
Partikül dışı şey farklı. Collision'dan farklı.
No, yes, okay, you see, your question was this one. If the wave function is oscillating, don't we have discrete energy values? My answer is no. One typical case is the free particle, where the wave function is oscillating, but it can have any energy. Here, positive energy solutions will be oscillating everywhere, but still they will have continuous energy values. They can have any energy.
Hocam, kurduğumuz denkleme göre dalga fonksiyonunun potansiyel enerjiye de bağlanması gerekiyor. İkisi de potansiyel enerjiye bağlı değil mi?
Well, you see, that's just a fixed, something fixed. My solutions will, of course, depend on what that U0 is. But in a given problem, the potential is fixed. It's not changing. But your wave function is changing from point to point. That's why we don't write that dependence on U0. But of course, if you change the potential energy, you are changing your differential equation and everything will change. Well, let's say I'm looking for E less than 0. This is assumed, or not as assumption. Like. I'm looking for such solutions. I'm not excluding the possibility of having positive energy solutions. They will exist. But these will be of interest. If energy is negative, I will define the energy to be minus h bar squared over 2m times some kappa squared with kappa squared positive. Or even I will even choose kappa to be positive. Now the above equation now becomes d squared phi of x by dx squared. This is equal to E times kappa squared times phi of x. It is positive. Now I can write my solution. Well, this is in region 1. Let me put an index I. Phi of I of x. So what is the solution? I have a function whose second derivative is a multiple of that function. Well, you see, if you have the sine and cosine, their second derivatives is true that it's a multiple of themselves, but with a negative coefficient. Here we have a positive coefficient. Well, multiplying an eigenfunction by a constant doesn't change the eigenvalue. Another function that is related with sines and cosines, exponentials. So this is just a times e to the power kappa x plus b times e to the power minus kappa x. This is the general solution. I have some boundary conditions though. I didn't impose very strict boundary conditions, but you see, we know that phi of x squared dx from minus infinity to infinity, this should be 1. I should choose a and b such that this can be made equal to 1. Well, that 1, at this point, I'm not interested in the exact value. What I'm interested in is this should be finite. Well, let's see. This is equal to, from minus infinity to 0, phi of 1 of x squared dx plus from 0 to L, phi of 2 of x squared dx plus from L to infinity, phi 3 squared dx. This should be finite, less than infinite. Well, let's forget about these for the time being. Let's look at the first term only. You see, I have this exponential. If this integral, why does an integral diverge? The integrand can be divergent. If the integrand, if what you are integrating has infinite values, the integral can diverge. Not all the time, but it can diverge. What is the second reason that an integral can diverge? You see, here, my integrand is finite. Whatever value x has, my integrand is finite. Now everything is defined over here. But you see, the range of integration goes to infinity. So I'm integrating a function over an infinitely long range. So it can diverge because the range is infinite. To make sure that it doesn't diverge, even if the range is infinite, I have to make sure that my function goes to 0 at infinity. So at this limit, my function has to go to 0 if I want my integral to be finite. Now let's look at over here. X goes to minus infinity. Kappa is positive. X goes to minus infinity. Kappa of x goes to minus infinity. E to the power minus infinity is e to the power minus infinity. 0. You can think of it as 1 over e to the power infinity. Any number, e to the power, a positive number to the infinity is always infinite. What about this one? X is negative, minus kappa times x is a positive infinity. E to the power infinite is infinite. So if this term is in my wave function, that tells me that this integral cannot be finite. So this term should be absent in my solution. So b should be equal to 0. So phi 1 of x is actually a times e to the power kappa of x. Since psi as x goes to plus or minus infinity should be 0. This is my boundary condition. So in this problem, my boundaries are at minus infinity and plus infinity. So my wave function in general has to satisfy this condition. Now, any questions here? Sorry? It should be 0. It should be 0. Otherwise, its integral will not be 1 or finite. Okay, we will pick up from here on Monday.